Scientists at CERN just confirmed something terrifying about the size of the universe. For 120 years, physics has been telling us a quiet lie about what we can actually see. Tonight, recent analysis of the Planck satellite data reveals that the observable universe, the 2 trillion galaxies, the 46 billion light-years in every direction, is not the universe. It is a tiny fraction of it, and the rest was hidden on purpose. The Nobel laureates who discovered cosmic inflation in 1981 warned us about this consequence. The same mechanism that made this universe livable also guaranteed that most of reality would be permanently invisible. Structurally, baked into the equations. Tonight we follow that mathematics all the way to the wall, and then past it as far as the physics will take us. The answer is not what you think. The answer is not nothing. What lies beyond the boundary is more universe than we can comprehend. Galaxies running on the same physics. Histories we will never read. And in the eternal inflation picture, something stranger still. Get comfortable. You are going to want to be here for all of this. Tonight, we follow that mathematics all the way to the edge, and then past it, as far as the equations will take us. Get comfortable. You are going to want to stay for all of this. There is a number so precisely calibrated, so impossibly exact, that when physicists first calculated what it should be versus what it actually is, some of them genuinely wondered if the universe had been constructed by something that understood what it was doing. That number is called omega. And omega does not describe the shape of a galaxy or a supercluster, or even the observable universe in the conventional sense. Omega describes the overall curvature of space itself, the geometry of the cosmos at the largest scale we can possibly measure. When the Planck satellite, the most precise cosmic measuring instrument humanity has ever built, returned its final data, the value it gave for omega was 1.00, plus or minus 0.005. In other words, the universe is flat. Not roughly flat, not approximately flat. Flat to within 0.5%, measured across a sphere 93 billion light-years in diameter. Sit with that for a moment. 93 billion light-years. A single light-year is 5.88 trillion miles. Multiply that by 93 billion. Across that entire expanse, across a volume so enormous that the human mind cannot form a sensory picture of it, we have measured the geometry of reality and found it balanced on a knife edge. That should disturb you, not in a frightening way, in the way a perfect magic trick disturbs you when you cannot figure out how it was done. Because flatness in cosmology is not a stable condition. It is not a resting state that space naturally settles into over time. It is the opposite of that. Flatness in the equations that govern the evolution of the universe is what physicists call an unstable fixed point. Think of it like balancing a pencil on its tip. You can do it for a moment with extraordinary care, but the slightest nudge in either direction sends it falling. And the longer time passes, the further from vertical it gets. The universe works the same way. If omega had started out even slightly above 1, even by a fraction, the self-gravity of everything in existence would have been just strong enough to win the war against expansion. space would have reached a maximum size and then collapsed back inward, ending in what cosmologists call the Big Crunch. We are talking about a universe that might have lived for a few 100,000 years, maybe a few million, before folding back on itself into nothing. No stars, no planets, no carbon, no anything with enough time to form, no one to ask what happened. And if Omega had started slightly below 1, the opposite catastrophe. Expansion would have won decisively. Space would have stretched apart so quickly that matter never had the chance to clump together under gravity. A universe of thinning gas spreading outward forever into a featureless, dark emptiness. No galaxies, no stars, no carbon, no you, sitting wherever you are right now, listening to this. The window between those two outcomes, between collapse and eternal dispersal, is extraordinarily narrow. And here is where the number becomes truly staggering. For the universe to look as flat as Planck measured it today, the initial value of omega at the very first instant, at what physicists call the Planck time, 10 to the power of -43 seconds after the beginning, would have had to be equal to 1 to within 1 part in 10 to the power of 62. Write that out. 1 followed by 62 zeros. That is the denominator of the precision required. That is how impossibly exactly the initial conditions of this universe needed to be calibrated for everything you see around you to exist. If the initial omega had differed from 1 by even a single unit in the 62nd decimal place, the universe would have either collapsed or dispersed long before a single star ever ignited. This is what cosmologists call the flatness problem. And calling it a problem is something of an understatement. It is not the kind of problem where you shrug and say the universe just happened to start that way. Because that answer requires you to accept that out of all the possible starting configurations for a universe, the one that actually occurred was so finely tuned that winning the lottery 17 times in a row looks like a statistical certainty by comparison. Physicists did not throw their hands up at this impossibility. They found a mechanism so extreme, so violent, and so brief that it left almost no direct trace in the observable universe, yet whose consequences are written into literally everything we can see. That mechanism is called cosmic inflation. Let us get specific about where you are right now. As you listen to this, you are sitting at the exact center of a sphere with a radius of approximately 46.5 billion light years. Not near the center, not close to the center, at the precise geometric center. And so is every other observer in the universe, no matter where they are. That is not a philosophical statement about human specialness. It is a direct consequence of how observation works in an expanding universe. And understanding it properly is the first step toward grasping just how much is hidden from us by the physics of inflation. The observable universe is defined by a simple constraint. The distance light has had time to travel since the universe became transparent, roughly 380,000 years after the beginning, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen and stop scattering every photon that tried to move. Before that moment, the universe was a plasma, an opaque fog of charged particles, so hot and dense that light could not travel freely through it. After that moment, photons were released and began their journey. The most ancient photons we can detect, the ones that have been traveling toward us since that very moment of transparency, have been in transit for 13.8 billion years. But here's where intuition breaks down. Those photons did not travel 46.5 billion light-years in 13.8 billion years by moving faster than light. Space itself has been expanding the entire time they were traveling. The universe kept growing while the photons were in motion, stretching the distance between their origin point and us. By the time they arrive, the object that emitted them is now about 46.5 billion light-years away. This is the difference between the light travel distance and the actual current distance, and it is crucial. The edge of our observable sphere is not 13.8 billion light-years out. It is 46.5 billion light-years out. Because the universe kept growing while the light was crossing it. Every observer in the universe, no matter where they are located, sees themselves at the center of their own sphere of this size. An alien civilization sitting in a galaxy near what we perceive as our observable edge has its own observable sphere, centered on itself, overlapping with ours in some regions, and extending far beyond ours in directions we cannot see. Their sky contains galaxies we have never seen and never will. Inside our sphere, the numbers are extraordinary. Recent estimates suggest there are approximately 2 trillion galaxies within the observable universe. 2 trillion. If you tried to count them at 1 per second, without stopping, without sleeping, without pausing for any reason, it would take you over 63,000 years to reach 2 trillion. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. And the Milky Way is, cosmically speaking, a fairly ordinary galaxy. Not the smallest, not the largest, just one of 2 trillion. The observable universe contains, by most estimates, somewhere in the range of 10 to the power of 24 stars. More stars than grains of sand on every beach and every desert on Earth combined, multiplied several times over. And yet, as we established, this is a tiny fraction of the total. The central thread running through everything we are exploring is the consequence of inflation. That the same mechanism which solved the flatness problem also pushed the overwhelming majority of reality beyond any horizon we can ever reach. Those 2 trillion galaxies are the local neighborhood. The full structure is something we can only infer from the physics, never observe directly. The boundary of our observable sphere has a name and a physical reality. It is called the cosmic microwave background, and it is one of the most extraordinary things in the sky. Not because of what it is, but because of what it tells us about the limits of our view. The CMB is the surface of last scattering, the shell of the universe at the moment it first became transparent. Every direction you look in the sky, if you could tune your eyes to the right frequency, you would see this glow. A nearly perfect black body radiation field at a temperature of 2.725 Kelvin, barely above absolute zero. The CMB is not the edge of the universe. It is a time boundary. The furthest back in time we can see using electromagnetic radiation of any kind. Beyond it, in every direction, space continues. The CMB is not where the universe ends. It is where our line of sight ends. For now. One of the most persistent confusions in cosmology is the idea that there is a single edge to the universe, a line somewhere out there beyond which nothing exists, or beyond which our telescopes simply cannot see.
The reality is more complicated and considerably stranger. There are actually several different horizons in cosmology, each defined by a different physical constraint, and they do not agree with each other. The particle horizon is what most people mean when they talk about the observable universe. It sits at approximately 46.5 billion light-years and marks the farthest distance from which light could have reached us in the history of the universe, accounting for expansion.
Anything within this sphere has at some point been in causal contact with us. But then there is the cosmic event horizon, which sits at a much closer distance of about 16.6 billion light-years. This is not the horizon of what we can see. It is the horizon of what we can ever interact with. The boundary beyond which, given the current and projected future rate of cosmic expansion driven by dark energy, any signal we send today will never reach its destination.
And any signal sent from beyond this point will never reach us. The Hubble sphere is different again. It sits at about 14.4 billion light-years and marks the distance at which galaxies are currently receding from us at exactly the speed of light. Inside the Hubble sphere, galaxies move away from us slower than light. Outside it, they recede faster than light. This does not violate relativity. It is space itself expanding, not objects moving through space. And then there is the future visibility limit, about 62 billion light-years in co-moving distance, which marks the farthest objects that will ever become visible to us as the universe ages, including photons currently in transit that have not yet arrived. Here is what ties all of these together. Right now we can see galaxies, some of them clearly in beautiful detail, that we will never be able to visit, never be able to communicate with, and that will eventually disappear from our sky entirely. Dark energy is accelerating the expansion of space. Over time, distant galaxies will redshift beyond detectability, their light stretching to wavelengths too long for any instrument to capture. The observable universe in causal terms is actually shrinking. Not in the sphere of past visibility is getting smaller, but in the sense that the set of objects we can ever hope to interact with is contracting. Inflation set the initial scale of what is hidden. Dark energy is continuing to hide more of it as time passes. Here is a question that sounds absurd on its face. How do you measure the geometry of the universe? Not the shape of Earth, not the curvature of space-time around a massive object, but the overall global curvature of the cosmos itself. How do you draw a triangle big enough to test whether the angles add up to 180 degrees or something different? The answer involves the cosmic microwave background, and it is one of the most elegant pieces of observational cosmology ever attempted. In a flat universe, the rules of Euclidean geometry apply at the largest scales. The angles of a triangle add up to 180 degrees. Light travels in straight lines that stay parallel. But in a positively curved universe, one with omega greater than 1, like the surface of a sphere, parallel lines eventually converge, and the angles of a large enough triangle add up to more than 180 degrees. The CMB gives us a ruler. In the very early universe, before the surface of last scattering, sound waves were traveling through the hot plasma. Pressure waves, driven by the competition between radiation pressure pushing outward and gravity pulling inward. These waves had a characteristic scale determined by how far sound could travel in the age of the universe at that time. When the universe became transparent and the CMB was released, those sound waves froze in place, leaving a pattern of slightly hotter and slightly cooler regions imprinted across the sky. The characteristic scale of those frozen waves, the distance between the peaks and troughs, is known extremely precisely from first principles of plasma physics. It acts as a standard ruler. If you know the physical size of that ruler, and you can measure the angle it subtends across the sky, you can calculate the geometry of the space through which its light has been traveling. In a flat universe, a ruler of a given physical size at a given distance will appear at a specific angular size. In a positively curved universe, it will appear larger. In a negatively curved one, smaller. The first major modern result came from the Boomerang experiment, a balloon observatory that circumnavigated Antarctica in 1998 and 2000, measuring the CMB at degree scales with unprecedented resolution. Boomerang found that the first acoustic peak in the CMB power spectrum sat exactly where flat geometry models predicted. Then came WMAP, which operated from 2001 to 2010. And then came Planck, the European Space Agency satellite that returned the most precise CMB data ever collected. Planck confirmed flatness at the level we have already discussed, omega equals 1 to within 0.5%. The acoustic peaks fell exactly where flat geometry models predicted. Independent confirmation came from baryon acoustic oscillations, the same frozen sound waves detected not in the CMB, but in the large-scale distribution of galaxies. The pattern of galaxy clustering across the universe carries an imprint of those early pressure waves, and that imprint, measured across surveys of hundreds of millions of galaxies, agrees with CMB flatness measurements to extraordinary precision. Let us go deeper into the mathematics of why flat is so dangerous, because it is easy to hear one part in 10 to the 62 and let it wash over you as just another big number in a field full of big numbers. It is not. It is something categorically different from other fine-tuning results in physics. And sitting with it properly is essential for understanding why inflation is taken so seriously by so many physicists. In standard Big Bang cosmology without inflation, omega obeys a specific evolution equation as the universe expands. The deviation of omega from 1 grows with time during the matter-dominated era, and grows even faster during the radiation-dominated era that preceded it. What this means technically is that omega equals 1 is an unstable fixed point in the dynamical equations. Just as the pencil balanced on its tip will always fall, a universe with omega even slightly away from 1 will evolve away from 1 over time. The deviation does not stay small, it grows. Run that equation backward in time. Today, omega equals 1 to within 0.5%. Go back 10 billion years to the era when the first stars were forming. Omega had to have been even closer to 1 at that point. Go back to the epoch of Big Bang nucleosynthesis, about 3 minutes after the beginning, when the first protons and neutrons were fusing into helium and deuterium.
At that point, omega had to equal 1 to within roughly 1 part in 10 to the 15th. Go back to 1 second after the beginning, 1 part in 10 to the 18th. Go back to the Planck time, 10 to the power of negative 43 seconds.
The earliest moment at which our physics can say anything meaningful about the universe. 1 part in 10 to the 62. 1 followed by 62 zeros. That is how closely omega had to match 1 at the beginning. Not as an approximation, as a precision requirement imposed on us by the equations of general relativity applied to the expanding universe. Is there a physical reason for this? Is there some principle that would naturally set omega to exactly 1 in standard Big Bang cosmology? There is not. There is no symmetry, no conservation law, no known physical mechanism that drives omega toward 1. It is purely an initial condition. And asking why the initial conditions were so precisely tuned is, in standard cosmology, like asking why a bullet fired from an enormous distance hit an exact target the size of a proton. There is no mechanism. You have to assume it was aimed. The flatness problem connects directly to the horizon problem, and the two together make the case for inflation almost ironclad. The horizon problem is this: the CMB temperature is uniform across the entire sky to 1 part in 100,000. Everywhere you look in opposite directions, regions that in standard Big Bang cosmology were never in causal contact, separated by distances greater than light could have crossed in the age of the universe at the time the CMB was emitted, the temperature is the same. How? Two regions that have never interacted cannot, in general, be expected to have the same temperature. If you put a hot cup of coffee and a cold glass of water on opposite ends of a very long table, and they never come into contact, they will not equilibrate. They will stay at different temperatures. Yet the CMB is telling us that the universe achieved thermal equilibrium across distances larger than any signal could have crossed. In standard Big Bang cosmology, this is simply inexplicable. Inflation solves both problems with the same mechanism. Before inflation, the region that would eventually become our entire observable universe was small enough, much smaller than an atomic nucleus, that all of it was in causal contact. Thermal equilibrium could be achieved. Curvature could be smoothed. And then inflation stretched this tiny, smooth, flat, equilibrated patch into something vastly larger than our observable sphere. 3 unsolved problems in classical cosmology. One mechanism that solves all 3 simultaneously. That is powerful. The story of inflation begins with a problem that has nothing to do with flatness or horizons. It begins with Alan Guth, a young particle physicist who, in the winter of 1979 and 1980, was working at Stanford trying to figure out why we had never detected magnetic monopoles. He was not thinking about cosmology in the grand philosophical sense. He was thinking about a very specific prediction of a very specific class of particle physics theories. The solution Guth arrived at, what he called in his research notes a spectacular realization, was that a brief period of exponential expansion in the early universe would not only dilute monopoles to undetectable concentrations, but would simultaneously solve the flatness problem and the horizon problem. He published in 1981, and the paper landed in the field of cosmology like a stone thrown into still water, sending ripples in every direction. The mechanism Guth proposed has been refined significantly since then, but the core idea remains. In the very early universe, the dominant energy was not matter or radiation, but the energy of a field. Specifically, what physicists call a scalar field, which Guth modeled as the energy associated with a phase transition in grand unified theories. This field was stuck in what physicists call a false vacuum, a state that is locally stable but not at the lowest possible energy. Think of a ball sitting in a shallow depression on a hillside, stable for the moment, but if it gets over the rim, it rolls down to the valley below. While the Inflaton field sat in this false vacuum state, it had a peculiar property. It acted like a cosmological constant, a form of energy that permeates space uniformly and does not dilute as space expands. This is the same kind of energy we associate today with dark energy, but at an energy scale roughly 120 orders of magnitude higher. An energy so extreme that it drove exponential expansion at a rate that makes the current cosmic expansion look essentially frozen by comparison. The expansion is genuinely exponential, not linear, not polynomial, but exponential, meaning space doubles in size in some fixed, very short time interval, then doubles again in the same interval, then doubles again. The number that emerges from the models for the total growth factor is at minimum around 10 to the 26th. Some models suggest far more. To get a feel for that number, if you took a single atom and inflated it by that factor, it would end up larger than the entire observable universe we see today. Andrei Linda, a Russian-American physicist who became one of the central figures in developing inflationary cosmology, introduced what became known as chaotic inflation in the early 1980s. Linda showed that inflation did not require exotic grand unified theory phase transitions. It could arise much more generically from a scalar field with a simple potential, an energy landscape where the field starts at a high value, rolls slowly downhill toward its minimum, and drives exponential expansion during the slow roll. Inflation ends when the Inflaton field reaches the bottom of its potential energy well, the true vacuum, and its energy is deposited into the particles of the standard model. This process is called reheating, and it is the moment that marks the beginning of the hot Big Bang as most people picture it. The fireball of matter and radiation that then evolved into galaxies, stars, and planets was not the beginning. It was what came after inflation ended. The Big Bang in this picture is not the creation of the universe. It is the thermalization of inflation's energy into ordinary matter. Reheating has observable consequences. The energy of inflation did not flow uniformly into matter and radiation. Quantum mechanics, which operates everywhere and always, introduced tiny fluctuations into the Inflaton field during its slow roll. These are not engineering imperfections. They are fundamental. The uncertainty principle guarantees that no quantum field can be perfectly uniform. The fluctuations in the Inflaton field were, during inflation, stretched from subatomic scales to cosmic scales by the expansion. After reheating, they became fluctuations in the density of matter, regions slightly denser and slightly less dense than average, spread across the universe at scales set by the rate and duration of inflation. These density fluctuations are what eventually grew under gravity into the large-scale structure of the universe. The filaments, sheets, and clusters of galaxies we see today, Planck measured the primordial power spectrum and found a spectral index of 0.9649, exactly where simple inflationary models predicted. But here is the line that ties all of this to our central story. Every fluctuation that inflation stretched to cosmic scales, every perturbation that became a galaxy, or a cluster of galaxies, or a cosmic void, each of these was once a quantum fluctuation smaller than an atom. Inflation is the mechanism by which the quantum becomes cosmic. And while it was doing that for the region that became our observable universe, it was doing the same thing for the vastly larger regions that inflation stretched beyond our horizon. Those regions contain their own quantum fluctuations, their own structures, their own histories. That we will never see. In 2011, 3 cosmologists, Vardanyan, Roberto Trotta, and Joseph Silk, published a paper that attempted to answer a deceptively simple question. Given everything we know, given the measurements from Planck and WMAP and the whole suite of cosmological observations, what is the minimum size the actual universe could be? They used a statistical framework called Bayesian model comparison, which is a rigorous way of asking which hypothesis is best supported by the data, while penalizing hypotheses that require many adjustable parameters. The number they arrived at is this. The universe must have a radius at least 251 times the radius of the observable universe. 251 times 46.5 billion light years. That gives a minimum radius of approximately 11.7 trillion light years. And the volume scales as the cube of the radius, so the minimum volume is 251 cubed, roughly 15.8 million times the volume of our observable sphere. 15.8 million observable universes, minimum, packed into the actual universe. 2 trillion galaxies in the observable universe. Multiply by 15.8 million. The minimum total number of galaxies in the actual universe under this conservative estimate is around 32 sextillion. That is 32 followed by 21 zeros. Every single one of them invisible to us. Not because our telescopes are too small, because inflation pushed them beyond the boundary of causal contact. And 251 times the observable radius is the lower bound. The number you get from the simplest inflationary models, assuming the curvature is at the edge of the observationally allowed range. Most inflationary models predict vastly larger extensions. There is a class of predictions under infinite flat universe models where the actual universe is genuinely infinite. Not very large in the way we might informally use that word, but infinite in the strict mathematical sense, extending without limit in every direction, with no boundary, no edge, no furthest galaxy. An infinite universe has a consequence that takes a moment to absorb. In an infinite universe filled with matter distributed roughly uniformly on large scales, every possible configuration of matter and energy will repeat. Not just once, but infinitely many times, including exact copies, including a Milky Way galaxy with a solar system and a planet and a species that built telescopes and is watching a video about the size of the universe. The distance to the nearest exact copy of our observable universe in an infinite flat universe has been estimated at roughly 10 to the power of 10
to the power of 118 meters, a number that cannot be visualized. Yet in an infinite universe, it is just a finite distance.
So far, we have been assuming that space beyond our observable horizon simply continues the way it does inside it, an ever-extending expanse, either infinite or at least vastly larger than anything we can see. Just more of the same stretching outward in every direction without end. But there is another possibility, one that does not require the universe to be infinite, and does not require it to have an edge. What if the universe is finite, genuinely, countably finite in volume, but has no boundary? What if space folds back on itself so that if you traveled far enough in a straight line, you would eventually arrive back where you started? It is a mathematically rigorous possibility that has been taken seriously by cosmologists for decades, and it connects to a distinction in mathematics that is worth understanding properly. The distinction is between geometry and topology. Geometry describes the local curvature of space. It tells you whether parallel lines will converge, diverge, or stay parallel. It tells you whether the angles of a triangle add up to 180 degrees or something different. Topology describes the global shape, how the space is connected at the largest scales. Not what happens between two nearby points, but what happens if you keep going in one direction for a very, very long time. The same local geometry can correspond to many completely different global topologies. Local flatness does not determine global shape. Those are separate questions, answered by separate mathematics. Take a flat, two-dimensional surface. The simplest topology for a flat surface is an infinite plane. But there is another topology. Take a square piece of paper. Connect the left edge to the right edge. You get a cylinder. Now take that cylinder and connect the top circle to the bottom circle. What you get is a toroidal, the surface of a donut. And here is the remarkable thing. That surface is still locally flat. If you lived on it and drew a small triangle, its angles would still sum to 180 degrees. But if you started walking in one direction and kept going, eventually you would arrive back where you started. The surface is finite. It has no edge, no boundary, no point where space simply stops. But it wraps around on itself in a way that makes it finite in area. Now extend that idea to 3 dimensions. A 3-torus, sometimes called a hypertorus, is the 3-dimensional analog of the same construction. Imagine a cube. Identify the left face with the right face, the top face with the bottom face, and the front face with the back face. If you walk through the right wall, you reappear through the left. If you float up through the ceiling, you drop back in through the floor. The space is locally flat. Every local measurement satisfies Euclidean geometry, consistent with what Planck measured, but globally connected in this looping, wraparound way. The universe would be finite in volume. It would have no center and no edge. And it would be, if you have ever played the original Pac-Man, exactly like that video game screen where walking off one edge brings you back on the opposite side. Except in all 3 spatial dimensions simultaneously. A toroidal universe would leave a specific fingerprint in the cosmic microwave background. If space loops back on itself at a scale comparable to, or smaller than, our observable sphere, then when we look out in certain directions, we would be looking at the same region of space approached from 2 different paths. The CMB temperature pattern in those directions would be identical. Cosmologists call these matched circles, and they are the definitive observational signature of a finite, topologically non-trivial universe. The Planck satellite looked for them. Its topology analysis searched the CMB sky systematically. It did not find them. But the non-detection is not a refutation. It is a constraint. Any topological identification scale must be larger than about 1.2 times the diameter of our observable sphere. There is a further consequence of inflation that takes us to the edge of what can currently be tested, and possibly past it. But before you tune out at the word multiverse, I want to be clear about something. What we are about to discuss does not begin with speculation. It begins with the same mathematics that makes inflation compelling in the first place. It follows step by step from the same quantum physics that produced the density fluctuations we measure in the CMB. The multiverse is not something cosmologists invented because it sounded exciting. It is something the equations keep insisting on, whether they are invited to or not. It is called eternal inflation. The leading class of inflationary models are called slow-roll inflation models. The name describes the behavior of the Inflaton field, the quantum field whose energy is responsible for driving the exponential expansion of space in the early universe. In these models, the Inflaton field starts at a high value on its potential energy landscape. Think of it as a ball sitting high on a very gently sloping hill, and it rolls slowly downward toward the minimum. While it is rolling slowly, its energy is high and relatively constant. That high, constant energy is what drives the exponential expansion of space. That is the classical picture. But quantum mechanics does not care about the classical picture. Quantum mechanics imposes something on top of the smooth classical rolling. It imposes fluctuations. The Inflaton field, like every quantum field, cannot be perfectly uniform and perfectly smooth. The uncertainty principle forbids it. So as the field rolls classically downhill, quantum fluctuations ripple through it constantly, randomly nudging the field value up or down around its classical trajectory. In most places and at most times, the classical rolling wins. The field moves downward and inflation ends on schedule. But here is what André Linde realized in the mid-1980s. In some regions of inflating space, the quantum fluctuations will not be small. They will, by random chance, be large enough to push the inflaton field back up the potential hill against the direction of classical rolling. Not most of the time, not even often, but quantum mechanics is probabilistic. And in the universe undergoing exponential expansion, rare events happen constantly. Because there is always more space being created in which rare events can occur. Here is why that matters. Inflation is exponential. Space is doubling and doubling and doubling again on timescales so short that the numbers barely translate into human concepts of time. In any given region, the chance that a quantum fluctuation kicks the inflaton field back up the hill, delaying the end of inflation in that region, might be very small, but the total volume of inflating space is growing exponentially. New inflating regions are being created faster than old ones are terminating. And in the regions where quantum kicks delay inflation's end, the same process applies again. The consequence, which Linde worked out carefully, is that inflation, once it starts, does not fully stop. It ends locally, in pockets, regions where the classical rolling won. the field reached the bottom of its potential, and reheating occurred. Our observable universe is one of those pockets. The hot Big Bang we think of as the beginning of everything is, in this picture, not a beginning at all. It is a local ending of inflation. The moment when our particular region of inflating space transitioned into a hot, matter-filled cosmos. But surrounding that pocket, and surrounding every other pocket, inflation continues. Each pocket universe begins with its own version of reheating, its own local Big Bang, its own initial conditions set by the specific state of the Inflaton field in that region at the moment inflation ended. String theory, the leading candidate for a theory of quantum gravity, predicts an enormous landscape of possible vacuum states. Different vacuum states correspond to different values of the physical constants, different strengths of the electromagnetic force, different masses for elementary particles, different values of the cosmological constant. The number of possible vacuum states that string theory's landscape contains is estimated at around 10 to the power of 500. In the eternal inflation picture, when a pocket universe forms and reheating occurs, the Inflaton field's energy is deposited into whichever vacuum state that region of space settles into. Different pockets may settle into different vacua, which means they would have different physics, different values of the fine structure constant, different electron masses, different strengths of the strong nuclear force, potentially different numbers of large spatial dimensions, different amounts of dark energy built into the fabric of space itself. They would be universes in the fullest sense, governed by their own physical laws, producing their own structures, or failing to produce any if their constants landed in regions of the landscape incompatible with complexity. The cosmic microwave background is the most studied object in all of cosmology. Not the most studied object in our solar system, or the most studied object in the Milky Way. The most studied object, full stop, in the entire history of human scientific inquiry. It has been mapped by 3 generations of dedicated experiments, each one more sensitive than the last. It has been analyzed by hundreds of independent research groups using every statistical tool that modern cosmology has been able to devise. And mostly, remarkably, almost breathtakingly mostly, it agrees. The standard cosmological model, with its flat geometry, its inflation-generated perturbations, its cold dark matter, and its cosmological constant, produces predictions for the CMB that match observation with a precision that should honestly make you stop and marvel at what physics has accomplished. The acoustic peaks sit exactly where they should. The spectral index of the primordial fluctuations matches the slow roll inflation prediction to within a fraction of a percent. The polarization pattern agrees with the temperature pattern in the way the physics demands. For a model built on events that happened 13.8 billion years ago in conditions we cannot replicate in any laboratory, the agreement is extraordinary. But not entirely. There are anomalies. They are small enough that no single one of them, standing alone, would compel you to abandon the standard model. But they are persistent, showing up independently in WMAP data and then again in Planck data, appearing in one analysis method and then again in a completely different one, sitting stubbornly in the numbers after every known source of contamination has been carefully removed. They are the kind of anomalies that serious scientists do not dismiss. Because the history of physics is full of cases where a small, persistent discrepancy in clean data turned out to be the first whisper of something genuinely new. The CMB cold spot is the most discussed. It was identified in 2004 by Patricio Villalva and colleagues using a filter called a spherical Mexican hat wavelet. They found a region in the southern CMB sky, roughly centered on the constellation Eridanus, that was anomalously cold. The region spans approximately 5 degrees across. In CMB terms, that is enormous, 10 times the width of the full moon. And it is cold in a way that goes beyond ordinary CMB variation. The probability of such a feature occurring by chance has been estimated at somewhere between 1 and 2%. The leading candidate explanation is a supervoid, a large region of space at a redshift of around 0.2, containing significantly below average matter density. When CMB photons travel through a void, they lose energy. They have to climb out of a shallow gravitational well as the universe expands and the well flattens, and they come out the other side slightly colder. Galaxy surveys have found evidence for an underdense region in the direction of the cold spot. But the supervoid does not fully account for the temperature deficit. The cold spot is still slightly colder than the supervoid alone predicts. And it has kept a small but rigorous community of physicists asking whether something else is contributing. The axis of evil is a different kind of anomaly, and in some ways a more unsettling one. When you decompose the CMB temperature pattern mathematically, breaking it down into components at different angular scales, the way you might decompose a musical chord into its individual notes, the largest scale components are called the quadrupole and the octupole. In a universe whose initial conditions were generated by inflation, a process that is by its nature completely isotropic, with no preferred direction in space, these components should point in random directions. They are not. The quadrupole and octupole were found to be aligned with each other to a degree that is statistically improbable. More striking still, both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sun. The probability of this occurring by chance in a genuinely isotropic universe is less than 1%. The anomaly was dubbed the axis of evil. Cosmologists have worked extremely hard to remove foreground contamination. The anomaly persists. Whether it is a systematic artifact or a genuine feature of the primordial CMB is a question that does not yet have a settled answer. The third anomaly arrived from a completely independent dataset, the large-scale distribution of distant quasars. A study using the Catwise catalog looked at the distribution of quasars across the sky and measured their dipole. The asymmetry between the number of quasars in one direction versus the opposite direction. The dipole measured in the quasar distribution is approximately 4 standard deviations larger than the CMB dipole predicts it should be. 4 sigma. That is not a rounding error. None of these anomalies have crossed the 5 sigma threshold required for a confirmed discovery. But none of them have gone away with better data either. Everything we have discussed so far has treated the size of the observable universe as a fixed fact, a number determined once and for all by the age of the universe and the history of inflation, stamped into the structure of spacetime and left there permanently. 46.5 billion light-years, 2 trillion galaxies, a sphere whose boundary was drawn in the first fraction of a second of existence and has not changed since. That is not quite right. The observable universe is not static, it is changing. And it is changing in a direction that makes everything we have been talking about,
the hiddenness of reality, the progressive inaccessibility of most of what exists, progressively worse with every passing year. It is called dark energy. And before we get into what it does to the future of the observable universe, we need to sit with what it actually is. Or rather, with the deeply uncomfortable fact that we do not really know. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. That sentence contains a word that should stop you. Accelerate. Not just expand, accelerate. The universe is not only getting bigger, it is getting bigger faster and faster, and has been for roughly the last 5 billion years. We know this because of supernovae, a specific type called Type 1a supernovae, produced when a white dwarf star in a binary system accretes enough mass from its companion to exceed a critical threshold and explode. These explosions are remarkably consistent in their intrinsic brightness, consistent enough that by measuring how bright they appear from Earth, we can calculate how far away they are with considerable precision. In 1998, 2 independent teams were using Type 1a supernovae to map the expansion history of the universe. Both teams expected to measure a deceleration. Instead, both teams independently found the opposite. The distant supernovae were fainter than expected. Fainter means farther. Farther at those distances means the universe was expanding more slowly in the past than it is today. Not decelerating, accelerating. Something was pressing the accelerator rather than the brakes, and had been doing so for billions of years. Both teams were sufficiently alarmed by their own result that they spent considerable time looking for errors before accepting it. They found none. The discovery won the Nobel Prize in Physics in 2011, awarded jointly to Perlmutter, Schmidt, and Rees, and it remains one of the most genuinely shocking results in the history of modern science. Dark energy currently accounts for approximately 68% of the total energy content of the universe. Most of what the universe is made of is something we have no confirmed physical explanation for. The simplest model for dark energy is Einstein's cosmological constant, which Einstein himself introduced into his equations in 1917, originally as a fudge factor to produce a static universe, then famously abandoned when Hubble's observations revealed the universe was expanding, then resurrected by the supernova results. In this model, dark energy is the energy of empty space itself. Quantum field theory predicts a vacuum energy density that is approximately 120 orders of magnitude larger than the value we observe for dark energy. 120 orders of magnitude. That is not a small discrepancy. That is the kind of discrepancy that suggests something is fundamentally missing from our understanding. This is the cosmological constant problem, and it sits at the center of theoretical physics as one of the deepest unsolved puzzles in the field. The results coming from the Dark Energy Spectroscopic Instrument, DESI, have attracted enormous attention. The first year of DESI data, released in 2024, produced a hint that dark energy's equation of state parameter may be evolving with time. A value that changes over cosmic history would rule out the simplest cosmological constant model entirely. Project this forward far enough, and the picture becomes almost desolate. In roughly 100 billion years, about 7 times the current age of the universe, the only galaxies remaining visible in the sky will be those gravitationally bound to the Milky Way, the local group.
a few dozen galaxies held together by their mutual gravity against the expansion of everything else. Everything beyond that will have faded to invisibility, redshifted into silence by the relentless expansion of space. Future astronomers, if any exist, will look out at a sky containing far fewer galaxies than we see today, with no way of knowing from their observations alone that the universe ever contained the 2 trillion we can currently count. The evidence will be gone. The universe will have hidden its own history. Let us step back from all of it, from the flatness problem and the knife-edge precision of 1 part in 10 to the 62, from inflation's exponential stretching and the factor of 10 to the 26th that it applied to space in less than a billionth of a second, from the CMB and its acoustic peaks sitting exactly where flat geometry models predicted, from the 251 minimum radius and the 15 million observable universes worth of content that implies, from the topological possibilities, the Hypertorus, the Picard horn, the Pac-Man universe wrapping back on itself at scales we cannot reach. Step back from all of it and look at what it adds up to. Because taken together, these threads do not form a collection of separate puzzles. They form a single, coherent story. And it is a story about something more specific and more strange than the mere size of the universe. It is a story about why the universe we can observe is not an accident of technology, not a temporary limitation of our instruments, not a problem that the next generation of telescopes will solve. It is a structural feature of how space-time itself is organized. The hiddenness of most of reality is not incidental to this universe. It is constitutive of it. The same physical process that made this universe livable, that smoothed out its geometry, seeded its structure, created the conditions for stars and planets and carbon and us, is the same physical process that hid most of the universe from us permanently. Not temporarily, not until better instruments arrive. The boundary was built into the physics at the same moment the physics built us. Our existence and our ignorance are not separate facts. They are 2 consequences of one event, separated by nothing more than the direction you choose to look at the equations. The observable universe is a causal bubble. That is the most precise way to say what it is. It is the sphere defined by the maximum distance from which any signal traveling at the speed of light through the expanding universe could have reached us in the entire history of time since the universe became transparent. Everything inside that sphere has had at some point the possibility of causal contact with us. Everything outside it has not. Not yet. And in most cases, not ever. Because inflation stretched those regions so far beyond our reach that the expansion of space will always outpace any signal they could send. This is where the holographic principle enters the story, and it enters it in a way that elevates the horizon from a mere observational limitation to something with genuine physical reality. The holographic principle was first proposed by Gerard Hooft and Leonard Susskind in the 1990s, growing out of work on black hole thermodynamics. The core idea is that all the information required to describe a volume of space is encoded on the 2-dimensional surface that bounds it. the way a hologram encodes a three-dimensional image on a flat surface. Juan Maldasena's work on what is called the ADS/CFT correspondence in 1997 gave this idea its most mathematically rigorous formulation, showing that a theory of gravity in a certain type of curved space is exactly equivalent to a quantum field theory living on its boundary. The two descriptions, volume and surface, are not approximations of each other. They are exact duals. Different mathematical languages describing the same physical reality. What this means, if you take it seriously, is that the horizon is not just a limit on what we can see. It is a limit on what physically exists in the information theoretic sense from the perspective of any observer inside it. So what lies beyond the wall? The honest, data-grounded answer has 4 layers. The first and most certain is simply more of the same. More space, structured by the same physics, seeded by the same inflationary perturbations, evolving under the same laws of gravity and electromagnetism and nuclear physics that operate inside our observable sphere. The minimum radius constraint of 251 times implies at least 15 million observable universes worth of content beyond our horizon, all subject to identical physical laws, all populated by galaxies and stars and whatever else those conditions produce, all permanently invisible to us. The second layer is finite topology, the possibility that space, rather than extending infinitely, loops back on itself in a multiply connected geometry. This would make the universe finite in total volume, with no edge and no center, locally flat in every neighborhood, but globally wrapped in a way that our current observations cannot detect. In this scenario, what lies beyond our horizon is eventually us, the same region of space approached from the other direction, the universe as a hall of mirrors, except the mirrors are so far apart that the reflection has never had time to reach us. The third layer is the extended inflationary volume, the full scope of what the inflationary epoch created, which goes far beyond the 251 minimum. Many well-motivated inflationary models predict expansion factors thousands or millions of times the minimum. Regions that were causally connected to ours before inflation, that shared the same pre-inflationary patch, the same initial conditions, the same early equilibrium, were pushed beyond our horizon during inflation and have been receding ever since. They share our history up to the moment of inflation. After that, we cannot say. They evolved under the same laws, seeded by the same quantum fluctuations. But their subsequent 13.8 billion years of history are inaccessible to us. The fourth layer is the multiverse, the foam of pocket universes produced by eternal inflation, potentially each with different physical constants, different vacuum states, different versions of the fundamental forces. Whether it is a scientific hypothesis or a mathematical extrapolation that happens to be consistent with observation is a debate that is ongoing and unresolved. Both things can be true simultaneously. And the discomfort of that is worth sitting with rather than resolving artificially in either direction. The equations reveal their own limits. The data tells us not just what we see, but how much we are not seeing. Cosmology has reached the point where its greatest achievement, its most precise and confident result, is a measurement of its own boundary. The wall was not built to frustrate us. It was built by the same process that built us. The inflationary epoch that flattened our region of space seeded the structure that became galaxies and stars and planets, and created the conditions for something like us to exist. That same epoch, in the same fraction of a second, drew the horizon that we will never see beyond. The observer and the boundary were created together. We are not separate from the thing that hides reality from us. We are a product of it. The observable universe is not a cage. It is a consequence. The question of what lies beyond it is not really a question about elsewhere. It is a question about why here exists at all. And the answer, as best the data and the mathematics can give it, is that here exists because the physics that made here possible also made everywhere else invisible. The universe has been explaining itself to itself through the only instruments it has ever produced that were capable of asking the question. We are those instruments. 2 trillion galaxies, and most of them forever beyond reach. Let that settle now, softly, without urgency. The equations have been speaking all night. They are quiet now. The flatness remains. The horizon remains. And you remain inside your causal bubble, at the center of everything you can ever know. 46.5 billion light years in every direction. That is yours. That is the window you were given by the same physics that made you possible. And beyond the window, more universe, more galaxies than you can count in 100,000 years. All of it running on the same laws, all of it silent from here. The wall was not built against you. It was built with you, at the same moment, by the same event. Let the expansion continue. You do not need to follow it tonight. Rest now. The cosmic microwave background still hums at 2.7 Kelvin in every direction. The universe is still here, and so are you. That is enough. The Inflaton field has settled. Reheating is long past. What remains is what always remains. Space. Expanding. Quietly. Somewhere beyond the horizon, a galaxy we will never name is forming its first stars. The physics is identical to ours. The outcome? Unknowable. Let the distance be distance. Let the darkness be darkness. Let the silence carry you now. The universe does not need you to understand it tonight. It only needed you to exist. And you do. Rest. 2 trillion galaxies, 32 sextillion beyond the horizon, and one mind somewhere on the third planet of a minor star, quietly letting go. There is no center to the universe. There is no preferred location. Every observer is at the center of their own observable sphere. This is not a coincidence. It is what isotropy means, written into the geometry of space-time. The Planck time is 10 to the power of -43 seconds, the earliest moment our mathematics can describe. Before it, the physics we know breaks down. What happened before is genuinely unknown. Not unknown because we have not looked. Unknown because the question may have no answer in our current framework. The baryon acoustic oscillations are imprinted in the distribution of galaxies across the entire observable universe. Frozen sound waves from the first 380,000 years stretched to cosmic scales, visible in the clustering of matter hundreds of millions of light years apart. Physics working the same way everywhere. The same frozen wave, the same ruler. String theory predicts 10 to the power of 500 possible vacuum states. Each vacuum state a different physics, each a different universe, if eternal inflation is correct. Most of them incompatible with complexity of any kind. The landscape is not a catalog of possibilities. It is, in the eternal inflation picture, a catalog of actual places. The CMB anomalies persist across independent analyses. The cold spot, the axis of evil, the quasar dipole. None of them definitive, all of them real. All of them sitting in the data quietly, waiting for an explanation that either arrives with better instruments or does not arrive at all. The Inflaton field rolled slowly down its potential energy hill for a fraction of a second. That rolling produced the density fluctuations that became every galaxy you have ever seen. Inflation is the mechanism by which the quantum becomes the cosmic, the smallest scale of physics reaching outward to the largest scale of structure. Dark energy is 68% of the total energy content of the universe. Dark matter is 27%. Ordinary matter, everything made of protons and neutrons, everything you have ever seen or touched or measured, is approximately 5%. The universe is mostly things we cannot identify. That is not a failure, it is an accurate result. The observable universe is not the cage, it is a consequence. The physics that made the wall also made the mind reading the wall. There is no outside position from which to evaluate the arrangement. You are inside the only universe you will ever have access to. That is enough. That has always been enough. Omega equals 1. To within 0.5% across 93 billion light years. That is the most precise measurement ever made of the largest thing that has ever been measured. The universe answered the question with extraordinary clarity. It is flat. From here, from inside this bubble, from the only position you will ever occupy. The observable universe is shrinking in causal terms. The set of things you can ever interact with is smaller tonight than it was when you were born. The dark energy has seen to that. By an amount no instrument can resolve. But the direction is certain. The process is irreversible. You are living at one of the earliest moments when the window is still wide. We are not separate from the thing that hides reality from us. We are a product of it. The inflationary epoch that drew the horizon also created the conditions for our existence. Our ignorance and our existence are not separate facts. They are two faces of one event, looked at from different directions. Every photon in the CMB has been traveling since the universe was 380,000 years old. 13.4 billion years in transit, arriving at your local space tonight, indistinguishable from the trillion other CMB photons arriving at this moment, each one carrying information from a slightly different point on the surface of last scattering. The holographic principle tells us that the information content of a region scales with its surface area, not its volume. The horizon is not just a limit on observation, it is a limit on information. What lies beyond it is real. But its information content, from our perspective, is encoded on the boundary between us and it. The universe will still be expanding when every star in the Milky Way has burned out. It will still be expanding when the last black holes have evaporated. The expansion is not ending. Only the visibility is. Only the window is narrowing. The physics continues, indifferent to whether anything remains to observe it.
You were made by the same inflation that made the horizon. You were made by the same quantum fluctuations that became the large-scale structure. You were made by the same dark energy that is slowly narrowing the window. You are not separate from any of this. You are the universe examining itself. The cosmic web of filaments and voids is the largest structure in the observable universe. The pattern traces back to quantum fluctuations of inflation, stretched to cosmic scale, frozen into the distribution of matter by gravity over 13 billion years. The web is a fossil of the first second of time, preserved at the scale of superclusters. The first stars in the universe formed somewhere between 100 million and 200 million years after the Big Bang. They were massive, hot, and short-lived. They exploded, seeding the universe with the first heavy elements: carbon, oxygen, silicon, iron. The atoms you are made of were forged in those first stellar furnaces and scattered across the galaxy long before the sun ignited. Every measurement we have ever made has been made from inside the observable universe. We have never had an external view. Everything we know about the cosmos has been inferred from local observations applied through physical laws we believe are universal. That belief is supported by the extraordinary agreement of the predictions with the measurements. You were made of atoms that were inside a star before the sun existed. The carbon in your cells was synthesized in a stellar core and expelled in a supernova before the solar system formed. The iron in your blood was forged in the collapse of a massive star. You are a temporary local concentration of the universe's matter, capable of turning around and looking at itself. Rest now. The physics will continue without your attention tonight. The expansion does not require observation. The quantum fluctuations do not require a witness. The galaxies beyond the horizon are forming stars and dying stars and doing everything that stars do, on their own schedule, in their own time, without reference to any mind inside this causal bubble. 2 trillion galaxies, each one 100 billion stars, each star a possible history. Most of those histories beyond our reach, all of them running on the same physics as yours. The quantum fluctuations that became you were once smaller than the smallest thing you can imagine. Inflation stretched them outward. Gravity gathered them. Chemistry organized them. Biology animated them. Here you are. Inflation lasted somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds. In that window, space grew by a factor of at least 10 to the 26th. Everything you will ever see or know or measure was contained in the region that grew. The Hubble constant describes how fast the universe is currently expanding. Different measurement methods give slightly different answers. The discrepancy may point to new physics beyond the standard model. Either outcome is interesting. The universe is still teaching us things.
Type 1a supernovae are called standard candles because their peak brightness is predictable. The two teams that discovered the accelerating expansion in 1998 were both expecting to measure deceleration. The discovery was not what anyone was looking for. It was what the data demanded. That is how physics works at its best. The Hubble sphere sits at about 14.4 billion light-years. Galaxies beyond it are currently receding faster than light. Not because they are moving through space faster than light, because space itself is expanding between us and them. Their photons are losing ground. But the Hubble sphere is growing. Some of them will eventually be able to reach us after all. Tonight you have traveled as far as the equations allow. You have stood at the edge of the observable sphere. You have heard about the flatness problem and the horizon problem and the mechanism that solved them both. You have followed the logic of eternal inflation to its conclusion. You have felt the weight of what dark energy is doing to the window. The wall was built on purpose, not by intention, by physics. The equations that allow matter to exist, that allow chemistry to occur, that allow complexity to arise. Those equations also guarantee that most of what exists will be permanently beyond the reach of anything that complexity produces. Now rest. The universe will continue its work. The expansion will proceed. The dark energy will push. The galaxies beyond the horizon will continue their histories without reference to yours. At every scale, you are held. Rest inside that. 2 trillion galaxies. And in the morning, they will all still be there, unchanged, running their physics, waiting for the instruments that will never reach them. And you will be here too, inside your causal bubble, at the center of everything you can ever know. You are the universe, examining itself through the only instruments it has ever produced that were capable of asking the question. That is what has happened here. That is enough. That has always been enough. Let that be enough tonight. The sky is a sphere of ancient light, all of it arriving now, all of it carrying the same message. The universe is here. It has always been here. You are inside it. Rest. The expansion continues. The horizon holds. You are still here. The physics persists. The void is vast. 2 trillion galaxies, all of them receding. The CMB still hums, 2.7 Kelvin, in every direction. The flatness remains, omega equals 1, to within 0.5%. Let that rest. The wall holds. The light is still traveling. 13.8 billion years, still arriving, still here. Breathe. The dark energy continues its work, quietly, relentlessly. You do not need to follow it tonight. The quasars are still burning, at the edge of what we can see. 13.4 billion light years away, beyond reach, beyond the horizon, beyond tonight. Let it be beyond. The Milky Way will merge with Andromeda in about 4 billion years. Almost nothing will collide. Space is mostly empty, even inside a galaxy. The void is the structure. The emptiness holds the web. The dark matter holds the galaxies. The dark energy holds the expansion. The physics holds everything. Even you, especially you. Rest. The universe does not require your attention tonight. It has been running for 13.8 billion years without it. It will continue. Long after every star has cooled, long after every black hole has evaporated, the expansion will still be here. The physics will still be valid. The equations will still hold, even in a universe with no observers. The equations do not require an audience, but tonight, you are the audience, and that is enough. Rest now. The observable universe is yours. 46.5 billion light years in every direction. All of it for tonight, quiet. All of it for tonight, yours. Let your mind drift as the cosmic fields expand in silence. Every galaxy you have seen tonight is just a momentary flare in the dark. The laws of physics do not require your attention to keep running. Space is vast, but it is also quiet, empty, and patient. The starlight that travels toward you has been on its way for billions of years. It is arriving now, carrying the peaceful history of the early universe. You are a part of this geometry, balanced on the same knife edge. There is no need to understand the equations to feel their stillness. The quantum fluctuations have settled into the structure of your world. Every atom in your body was once forged in the furnace of a dying star. We are all made of starlight, returning slowly to the cosmic background. The expansion continues, drawing a gentle horizon around your thoughts. Nothing in the universe is lost. It simply changes its form and rest. The CMB photons carry the echo of the first light, quiet and cold. The gravity of the cosmos holds everything in a slow, eternal embrace. Let the details of the day fade like distant, red-shifted light. The observable universe is a bubble of time holding you safe tonight. There is nothing more you need to calculate before you sleep. The mathematics of the universe is consistent, stable, and silent. The cosmic web connects the furthest structures in a quiet network. Rest in the knowledge that the laws of nature are keeping watch. The flatness holds, the expansion slows, and the starlight remains. The flatness problem was solved in the first fraction of a second. Everything since has been the long aftermath of that solution. The horizon is not a wall. It is a relationship between the speed of light and the age of the universe and the rate of expansion. You are inside it. That is all. Somewhere beyond the observable sphere, the physics is identical. The quantum field theory is the same. The general relativity is the same. The constants are the same. Everything is the same, and none of it is reachable. The CMB photons have been traveling for 13.4 billion years. They are still arriving, right now, from every direction, carrying the oldest information in the universe. Omega equals 1. The universe is flat. The knife edge held. Something made it hold. We call that something inflation. We do not know what inflation was made of. 2 trillion galaxies, each one 100 billion stars. Each star a nuclear furnace. Each furnace seeding the void with heavy elements. Each element a building block. Each building block
part of something.
The dark matter does not interact with light.
It cannot be seen. It can only be inferred from the motion of the things it surrounds. It is most of the matter. It is everywhere. It is unknown. Dark energy is 68% of everything. It has no known physical explanation. The cosmological constant problem is the largest discrepancy between prediction and observation in the history of physics.
The acoustic peaks in the CMB power spectrum sit exactly where the flat universe model predicted they would sit. That agreement is one of the most precise confirmations of a theory in the history of science. Baryon acoustic oscillations are frozen in the distribution of galaxies across the entire observable universe. The same sound wave, stretched to the scale of hundreds of millions of light years, still visible in the data. The spectral index of the primordial power spectrum is 0.9649. The slow roll inflation prediction is a spectral index slightly less than 1. The agreement is extraordinary. The Hubble tension remains unresolved. Two different measurement methods give two different values for the expansion rate. The discrepancy is real. The explanation is unknown. The universe is still teaching. The cold spot in the CMB is still colder than the supervoid alone explains. The axis of evil persists across independent analyses. The quasar dipole is 4 sigma. The universe has not yet finished speaking. Eternal inflation is not a speculation. It is a prediction. It follows from the quantum mechanics that produces the CMB fluctuations we measure. The equations keep insisting on it. Whether it is testable is another question. String theory predicts 10 to the 500 vacuum states, each a possible physics, each a possible universe. If eternal inflation is correct, most of them are occupied. None of them are reachable from here. The holographic principle says the information content of a volume is encoded on its boundary. The boundary is real. The horizon is real. The encoding is real. We are inside the encoding. ADS/CFT correspondence shows that gravity in a volume is equivalent to a field theory on its boundary. The two descriptions are exact duals. The universe may be a hologram of its own horizon. Inflation stretched quantum fluctuations to cosmic scales. Those fluctuations became density variations. Those density variations became galaxies. You are made of atoms from one of those galaxies. You are a quantum fluctuation that learned to ask about quantum fluctuations. The Big Bang was not an explosion into space. It was an expansion of space. There is no center it came from. There is no edge it expanded into. There was only before and after. And we can only see the after. The Planck satellite has finished its work. Its data will be analyzed for decades. Every anomaly it found will be pursued. Every confirmation it gave will be built upon. The most precise map of the early universe ever made. Already complete, already in the archive. The future visibility limit is 62 billion light years. That is the farthest an object can be today and still eventually send us light. Beyond that, even light currently in transit will never arrive.
The window is finite, and it is smaller than the universe.
In 100 billion years, the sky will contain only the local group, the Milky Way, Andromeda, the Magellanic Clouds, a handful of dwarf galaxies. Everything else will have redshifted into silence. The universe will have hidden its own history.
The last black hole will evaporate by Hawking radiation at a timescale of 10 to the 100 years from now.
After that, the universe will be cold, dark, and featureless. The expansion will still be happening into a void that contains no observers to measure it.
You are here at a cosmologically fortunate moment.
Early enough that 2 trillion galaxies are still visible. Early enough that the CMB is still detectable. Early enough that the evidence of inflation is still legible in the data. Later observers will inherit a smaller window.
The wall was built by the same event that built you.
The inflationary epoch that drew the horizon also created the conditions for your existence. You did not come after the wall. You came with it. You and the wall are the same event.
The observable universe is a causal bubble.
Everything inside it has been in causal contact with you at some point. Everything outside it has not. The boundary is not physical. It is informational. It is made of the finite speed of light and the age of the universe.
There is no outside position from which to view the arrangement.
You are inside the only universe you will ever have access to. That is not a limitation to be lamented. It is a description of what observation means when the observer is part of the system. Rest now. The equations have been speaking all night. They are patient. They will still be here when you wake. The flatness will remain. The horizon will remain. The physics will remain. Unchanged, consistent, exact.
The universe does not know you are listening. It does not need an audience.
It has been running its physics for 13.8 billion years without one. Tonight, you were the audience. That is enough. 2 trillion galaxies, and most of them forever beyond reach. Let that settle.